learning for theorem proving, well, really interactive theorem proving. I would try to avoid as many technical details as possible, because I think the traditional logic audience is perhaps not very familiar with both of these topics, both machine learning and interactive theorem proving. So I would just try to give you a big picture. But if there is still something you find confusing, please interrupt me as you wish. Okay, so I will first try to give a gentle introduction to interactive theorem proving. Then I will talk about the automation of interactive theorem proving by machine learning. So this is a recent project of mine called Tactic Zero. It is basically using the deep reinforcement learning, well, end-to-end deep reinforcement learning to learn to do interactive theorem proving, or say to develop automation in an interactive theorem prover. Then I will talk about the challenges in this field. So what the problems are and what the future work would be. Okay, so this is a big picture of interactive theorem proving, and so you can see that on the left half of the this screenshot. So this is how we do interactive theorem proving in an interactive theorem prover called Ling. You can see on the left half of the screen there is the theorem stated. This is the quadratic reciprocity theorem, and you can see that there's the proof there. You can see these keywords have, from, by, whatever. And on the right half of the screen, there is where the machine prompts you the current proof state. So you can write something on the left half of the screen, say have HPQ, PZ mod Q is not equal to 0. And after you write that, the computer will let you know what's left, what you need to prove right now. And by so this is kind of the interaction, what we call interaction between the human and the computer. So you fill in some sort of details, a bit proof steps, and the computer will let you know what the remaining goals are and what you need to do next. Okay, so this is, or maybe let's just explain a bit about the theorem here. You can see that this is the standard form of the quadratic reciprocity theorem. So it is implicit here that P and Q are primes. And we have the fact that P and Q are all numbers, and P is not equal to Q, and then we have the Legendre symbol, so of P and Q times P and Q, and then it equals that thing. And below is all the proofs. You can see that it is in a relatively readable form, well, human readable form, rather than so it is not like the kind of automated theorem proving you see, like the decision procedure for whatever, like SMT solver for first order logic or whatever. So they usually output a chunk of formula that's not really readable by humans, right? Okay, so how does this work? So we have like two styles of interactive theorem proving. The first is what we call the term style. So the way we do this is by Curry-Howard correspondence. Theorem proving is really just about constructing terms of certain types. So for example, in this one, this is a statement of, well, it's a really simple propositional statement. It says P implies Q implies P. And to prove that, so we only need to construct a term of that type. So this is a proposition, but it is also a function type, right? So it is you can think of it as some type in simply typed lambda calculus. It is P implies Q implies P, and you just need to construct a type of that. You just need to construct a term of that type. In this case, it's lambda H1, H2, H1, right? So this is a term that has that type. And you can see that what we are constructing here is really just a program, rather than, you can think of it's just a program that takes two arguments, H1 and H2, and it returns you the first argument, H1, right? So in this sense, we say that theorem proving is really the same thing as program synthesis, well, functional program synthesis, because the statement here is the type, and the proof here, you can see this thing is really the program that we constructed. Okay, so but this kind of term style theorem proving is tedious because you have to fill in every detail of the lambda term, right? So sometimes you don't want to do that, especially when the statement here gets more complicated. So we have the tactic style theorem proving. So this is one step further. So we say that term style is really tedious. We want to automate this process and develop some sort of programs, well, meta programs that can help us construct these lambda terms. So for example, in this same example can be written as this by intros assumption. So what we mean by intros here, so this intro is called a tactic, and what it does is that it introduces everything that can be introduced by looking at the type, right? So you know that this type has two arguments, so you can, what the interest does is it introduces these two binders, H1 and H2. And after you introduce these two things in your context, so what we did here is that we say, I look into my context and I find this H1 that matches exactly the type, the return type, right? But you don't really need to do it by yourself. You don't need to do it manually. You can say that I will write a simple program that automatically looks into the context and find one that matches the return type. So you don't have to fill in by hand. So this is another tactic which we call assumption. It basically looks at what we've introduced and try to find one assumption that matches the conclusion. So this is what we call the tactic style theorem proving. And in case the target theorem is simple enough, or we have certain domain-specific decision procedures for that, we can develop even more advanced tactics such that such like this auto. So what this auto does is that it implements the decision procedure for propositional logic, and it will solve the goal directly. Okay, so the machine learning for theorem proving will be based on this tactic style theorem proving, because we know that, because you can see that it's it doesn't really care about the details there. It's all kind of the high level theorem proving that's closer to the human pen and paper proofs, right? Okay, so we can also classify the interactive theorem proving by the underlying type theory. So there's one sort of them that uses simple type theory or higher order logic. So these theorem provers are Ho4, Holite, Isabelle, and the characteristics of this kind of interactive theorem proving engine is that theorems, they are easy to automate, but they are less expressive. They cannot really express algebraic structures very elegantly. So for example, you cannot really say, I want a vector of certain length. That cannot be a particular type because it depends on the length of the vector. On the other hand, we have these theorem provers that uses strong type theory, mostly calculus of inductive construction. So we have Koch, Lin, Agda, and the advantage of this kind of theorem prover is that they are super expressive. They can, because they have dependent types, they can express the algebraic structure very elegantly. But the problem with those is that they are very difficult to automate, because once you have those strong type systems, everything becomes almost undecidable. So you cannot really like do type inference, type checking, whatever. So it's really difficult to write automation for that, because recall that the automation, what we mean by automation here is we need to construct the lambda terms for those things, and then do the type checking to make sure that the lambda term matches the type of the statement. But once we have a very strong type theory, this kind of automation becomes also difficult. Okay, so what we mean by automation here is really the traditional logical methods. You can think of it as rewriting, simplification, elaboration, or the domain-specific decision procedures for whatever theories you have. Machine learning, automation by machine learning is not in this category, and we will see that machine learning doesn't really care about what kind of type theory you use here. Okay, so I think some of us may already be familiar with the automated theorem proving, but I just want to emphasize that there's a difference between interactive theorem proving and automated theorem proving. Well, although sometimes both of them are called automated theorem proving, because once you develop the automation for interactive theorem proving, it becomes automated theorem proving, right? But there is still some key differences. The first is that interactive theorem proving requires intensive human input, while automated theorem proving does not. So automated theorem proving just does what it does. And for interactive theorem proving, most of the proofs are written by a human. The second is that in interactive theorem proving, we usually have a strong background theory, and in automated theorem proving, we only deal with weaker theories. For example, in Lin, the background theory has a proof theoretic strength at roughly ZFC plus there exists in many inaccessible cardinals. While for automated theorem proving, we usually deal with theories like first order logic, equational logic, arithmetic, bit vectors, arrays, these specific theories, which we know that there are sophisticated decision procedures and they can be efficiently automated. So the third point is that in interactive theorem proving, we have this kind of high-level proof language, just as what we saw here. Like you can see that there's keywords, there's relatively readable proof scripts. But in automated theorem proving, it's not the case. You will usually see a bunch of unreadable, unparsable logical formulas. So the fourth point is that we have trustworthy code base of interactive theorem proving, and on the automated theorem proving side, the code base is relatively error prone. So this is because, as we said, interactive theorem proving ultimately boils down to type checking, right? So you only need a very small type checker for your system to work. But for automated theorem proving, the code base is really large because they have to be efficient. There's a bunch of optimizations that you can implement for your theorem proving, and those usually include legacy code or whatever, and they're really error prone. And the last point, but not least, is that interactive theorem proving is relatively inefficient, but automated theorem provers are highly efficient. This is because still it's about type theory, because computing in interactive theorem proving is like the beta reduction of type theory, right? So you have all these symbolic computation that you need to do. So even computing like 3 plus 2 is expensive because it's not it is not native integers, but a bunch of SS0 plus SS0 or whatever. So it's inefficient, but in automated theorem proving, it's not. It's highly efficient because those are, you can use whatever programming language you like. In C++, you have native integers, you have native data types, and that makes things efficient. Okay, so just to give you a bit more sense on what we have, so what's the current interactive theorem provers can do. So these are the things that I have done in interactive theorem proving. So I formalized the infinite Ramsey theorem. So this is, I think you're familiar with this. I formalized cross-code tree theorem. This basically says that the set of finite trees is well quasi-ordered under homomorphic embedding. So I have a verified decision procedures for model logics with optimizations. So the way we did it is that we implemented these decision procedures as functional programs, and we verified the correctness of these functional programs with respect to crypt key semantics. And I've also contributed to the Lean standard library where we have those finite sets, and I formalized the Turing reducibility just so we've just seen in Junlei's talk. So we don't have the full Turing reducibility yet, so we don't have Turing degrees, but we have many 1 degrees, and we have one degrees, and we prove that they form a percent lattice. And we have this sort of tactics, but you're probably not interested in that. And we develop a link between Mathematica and the link, so we can perform numerical computation in Mathematica and import it to link and vice versa. So none of these, so these are interesting projects, but none of these are really as significant as follows. So this on December 5th, 2020, Peter Schultz challenged anyone to formally verify some of his recent work with Dustin Clausen. So Peter Schultz is one of probably one of the most greatest modern mathematicians. So, and the Lean community led the response and on June the 5th, 2021, Peter Schultz acknowledged the achievement. What he said is the following. So exactly half a year ago, I wrote the liquid tensor experiment blog post challenging the formalization of a difficult foundational theorem from my analytic geometry lecture notes on joint work with Dustin Clausen. While this challenge has not been completed yet, I'm excited to announce that the experiment has verified the entire part of the argument that I was unsure about. I find it absolutely insane that interactive proof assistants are now at the level that within a very reasonable time span, they can formally verify difficult original research. And this is the current level of interactive theorem provers. Okay, so now we are ready to talk about the machine learning part. So as we've seen that we've already seen that the to do interactive proving, you have to provide a great amount of details, even if you use those tactics. So, what we want to do here is that we want to fully automate this process. We want to fully automate mathematics, but there is still a long way to go. The goal is to develop automation for interactive improving with machine learning, and the system we use here is HO4, and the proof style here is tactic, and the approach here is end-to-end deep reinforcement learning. So as we've just seen, so the interactive theorem can be split into 2 steps. The first is that we perform tactic selection and the premise selection. So we will, given a goal, we will need to choose the proper tactics that we can apply to that goal. And many tactics also take arguments. So you can think of it as taking the possible lemmas that you will need in order for that tactic to work. So for example, we can perform simplification using certain lemmas. If you have A equals B and we have a lemma says B equals C, then by performing simplification, we can have A equals C, right? So, but in this case, you will need the lemma B equals C, right? So that is something you need to provide to the tactic. So the first step is that given a goal, we need to perform tactic selection and premise selection. This is the first part of interactive theorem proving. So a tactic application may discharge the target goal completely, which means that your tactic completely solves the goal, or it may generate a new set of sub-goals. So this is just like what you have, or what you may see in pen and paper proofs, right? You apply a lemma and you have something new to deal with. So that is the first part. The second part is what we call proof search. So basically what you do here is that you repeatedly apply tactics and you will keep having new goals, or you will have all the goals unsolved. But very often you will have meaningless goals generated, or you will have undealable goals generated. It's just much like you have your pen and paper proofs. You did something wrong and you want to restart your proof. So in that sense, we say that we need a decent proof search. So you will have all the branchings, which is the possible tactics that you can apply. And after applying each of these tactics, you will have a bunch of goals newly generated, and you can keep doing this. So you will have a nice tree structure of your proof, right? Just like what you do in pen and paper proofs. So we will need a mechanism to manage that kind of proof search. So you can do it with breadth first search, best first search, depth first search, whatever. But here we will try to learn such proof search. So yeah, so what's important here is that the wrong tactics may generate meaningless goals and make proof search untractable. So one thing you can think of is that you can perform induction. Say we have a fairly easy arithmetic goal, and you can perform induction over and over again, right? You can do induction on n, and you have your inductive hypothesis in your inductive step. And in your inductive step, you can still apply the induction again. You can do this infinitely many times, and you will never get your proof, right? So we will need a mechanism to detect kind of states and help you avoid that situation. So there have been learning-based systems for interactive theorem proving. We have Tactic-Toe, Deep-Hole, and the GPTF. So they all use different approaches, but the one of the common characteristics is that they all use a fixed proof search. This one is Monte Carlo tree search. This one is breadth first search. This one is best first search. So the most successful one is this GPTF. It is for MetaMath and Ling. It uses language models plus best first search. What we mean by language models here is that it treats interactive theorem proving, or it treats the general theorem proving in math as a natural language or as a neural translation problem. You can think of your Go as the source language, and you can think of your proof step, or more generally your proof, as the target language. Then it's just a string-to-string translation, right? It's like you translate from Dutch to English, right? So, and this is currently the most successful one that we've seen, but the problem is that they still use a best first search, and that is very expensive in time and space. And so what we do here is that, so the motivation of my project Tactic Zero is that we notice that this mainstream approach has these characteristics. The first is that they learn from human example proofs. The second is they have a separate fixed or prescribed proof search procedure. And due to these two things, we have potential limitations. The first is that the first is technical. So if we learn from human example proofs, then the quality of the agent, the quality of your automation depends on the quality of human proofs in the library. So what we mean by that is that the proofs in the library are not optimal, are not the shortest. They are not. They only reflect the particular knowledge of the author, right? So different human author may have different proofs, but in the library you only see one of them. So so the agent you train is likely to be biased. So the second is that there is only small amount of training data, right? Human proofs are rare resources, and there are only thousands of proofs in the library, but this is just a too small amount of data that you can use to train the neural network. Usually you need much more than that, millions data for the training of a language model. And the third is that the tree search, such as breadth first search, is very expensive in time and space. And it is unnatural. So conceptually, human experts do not prove theorems that way, right? You don't really do the breadth first search when you prove mathematical theorems. You have your intuition, right? So we kind of we want to model that kind of behaviors. Okay, so the problem is that would it be possible to have a framework that learns to prove theorems without human examples and learns proof search strategies by itself? So this is the motivation that we want to develop the Tactic Zero. And how is this possible? So we can think of the decision process. So say we want to prove a very simple theorem, P and Q implies P and Q. So what we are describing here is that we try to model the process of theorem proving as a Markov decision process so that we can apply reinforcement learning. And this is an example here. So we start with the original goal, P and Q implies P and Q. So how to prove this thing? So one thing you can do is that you can introduce the assumptions, in this case, P and Q. So what you have here, it becomes P and Q in your context, and you want to prove P. And so this can be done by a tactic called strip tag. So this is probably a bit too technical for this audience, but let me just try to express this, try to explain this. So so we will have a let's first introduce a concept called fringe. So what a fringe is that it is well, how do we say this? So at any point of your proof attempt, you will have a set of goals that you need to solve in order to solve the original goal. So once you solve this set of sub-goals, you will be able to solve the original goal. So in the case of the original goal itself, you just need to solve the original goal, right? So once you apply some tactics, you generated some new goals. And then if you're able to solve this set of new goals, then that is equivalent to saying that you solved the original goal, right? So in this case, fringe one, if you look at this fringe one, if you solve every goal in this fringe, then it is equivalent to say that we've solved the original goal, right? It's the same. Then if I apply some new tactics, say induction, on this new fringe, on one of the goals in this new fringe, we will generate something new, say this fringe 2, and then if I solve every goal in this new fringe, then I solve the original goal, right? By doing this repeatedly, we will have a bunch of fringes generated, and solving each of these fringes completely, meaning that if we are able to solve every goal in that fringe, we will solve the original goal, right? So now, what is a state in this case? A state is a set of fringes, and if we are able to solve one of these fringes, we will solve the original goal, right? So this set of fringe is a state in the Markov decision process. So, and our actions is that given a state, we will choose a fringe to deal with. This is similar to say that we are trying to identify which set of sub-goals are easier to solve. And then we will choose one particular goal in that fringe to deal with, and we apply some new lemmas, new proof step to that, and we will generate something new, and that gives us the next state. And we'll keep doing this until we reach a empty fringe, in which case we say that we know that the original goal is solved, and we can recover a proof of that. Okay, now what is our MDP? What is our Markov decision process? So state, we will define a bunch of components that we need for the Markov decision process. The state is a set of fringes. And action is a for tuple ijtc. Intuitively, I is the ith fringe in a state, j is the jth goal in the fringe, t is the tactic, and c is the arguments to that tactic. And we will design the reward. So a good thing about an interactive prover is that the prover is able to tell you, to give you feedback after every step of tactic application. So it will tell you whether the tactic is applicable, or whether it discharges the goal entirely, whether it approves the goal entirely, whether it leaves you new goals to be proved, or whether the tactic times out. There's just not enough time to solve the goal. So for each of these different states, for each of these different feedback, we will assign a reward, which is a real value that tells you how good the proof step is. And the transition of the Markov decision process is that we will replace the original goal in the old fringe by newly generated sub-goals, and then we add the resulting fringe to the previous state. So this is basically says that how do I go from one state to another state? How is new state generated? Termination. So when does the Markov decision process terminate? When an empty fringe is generated, which means that we reached the QED of the proof, or when the time step budget is exhausted. So say we only allow maximum, like say 50 steps, and if the agent is not able to find the proof in 50 steps, then we say that you are failed. You can start a next attempt, and we will do it again. So solving the MDP, so this is going to be a bit more technical, but what you just need to know is that there is the sort of learning algorithm. So once you've defined the Markov decision process, there is the learning algorithm in reinforcement learning that can solve this MDP. So just let me just quickly go through this. So we will have an encoding. So the expressions, your goals, your tactics are really just the strings, right? So you can, machine learning algorithm doesn't really work with these plain strings. You have to encode them into numeric representations. So what we do is that we tokenize each whole-for expression. You can think of it as your logic formulas. We tokenize them and we represent them in Polish notation. And each expression is then represented by a 256-dimensional vector learned by a transformer-based autoencoder. So you don't need to know what this is, but you can think of it as a black box that takes a string and returns you something that's a 256-dimensional vector. And so the first thing we need to do is we need to perform fringe selection. So given a state, we need to select one particular fringe in that state. So that we can go further, right? So what we do here is that we develop a neural network. So you can think of it just as a function that takes a goal, which is a 256 vector, and it returns you a real. This, you can think of this as the score of that goal. So the idea here is that a fringe is essentially just a set of goals, right? To assign a score to a fringe, so we just need to assign score to each goal in that fringe, and then we can sum them up to represent the score of that fringe. So this exactly says that after our neural network predicts a score of that goal, we sum them up, and we say that is the score of our fringe. Then given a state, we will have a bunch of fringes, and we will have a bunch of scores associated to those fringes. Then we will do a softmax to give us the probability of choosing each of these fringes. So this is, you can basically think of this as a function that takes all the scores and it returns you a bunch of probabilities of choosing those fringes. Then once we have the fringe chosen, we will by default attack the first goal in that fringe. So this is because every goal in that fringe needs to be solved, and it doesn't matter which one you do first, right? So we will just take the first, and then given that first goal, we will do the tactic selection. So again, it's just a function that takes a goal and returns us a RD. Why is it RD? Because we will, so in a interactive improving system, there is always a finite number of tactics that you can choose from. Let's say we have D of them. So the V tactic gives us an array, which is RD, an RD vector, which represents the scores of each of the tactics that we have in hand, right? So this is basically scoring all the tactics we have. And again, we perform a softmax, which returns us the probabilities of choosing each of these tactics. So once we've chosen tactics, we select the arguments. So this is, you don't need to know this, but we just need to know that it computes a bunch of probabilities of choosing each arguments depending on the previously chosen goal, the previously chosen tactic, and the previously chosen arguments. So it can take not only one argument, but a list of arguments, right? It's just like that when you try to prove a theorem, you can have a bunch of lemmas instead of one lemmas. But once you've chosen the first lemma, your next lemma usually depends on the first lemma you've chosen, right? So this is what we call the autoregressive generation of tokens. So it basically says that the next element you choose, this depends on the previous element you choose. Okay, So now we have a bunch of probabilities: the probability of selecting fringe f given state S, the probability of choosing tactic T given our state and our goal, and the probability of choosing the ith arguments given the state, goal, and tactic and the previously chosen arguments, right? So we have a bunch of probabilities. Then we can apply the algorithm called policy gradient to optimize our policy. What is a policy? A policy is essentially a given state. We need to choose an action, right? So we've defined what the state is and what an action is. And we just need to compute the probability of given the state and the probability of choosing that action. And it is defined as the product of the bunch of components, the probability that we've just computed. And our objective is the expected rewards. So after you perform each action, we will set that there's a bunch of reward that you will receive. And the goal is to maximize the reward the agent receive. And if the proof is found, we will assign a very large reward for that. So our agent will be able to, because the reward is that large, it will always try to move to the direction that is more likely to lead to a proof of that goal. Okay, so this is experiments. So we fix a set of tactics that can be used by the agent. We take 1,342 theorems from Hofor's core library, and those theorems are all known to be provable using the same set of tactics. And we reward the agent for making little progresses. So if it is able to find, if it applies a tactic that generates new goals, we give it a small reward. Otherwise, we will always have a small negative reward for each action. So we prevent it from cheating. This is a bit of details that you're probably not interested in. It's related to interactive improvers. We also have a replaying mechanism to help overcome sparse positive rewards in the early training phase, because the policy starts with random. So you're basically randomly exploring the steps that can make a proof work. And this process is really difficult because sometimes you are able to find a proof and later you are never able to find a proof again. So we will develop a replaying mechanism that help the agent to recall the previous success it had with the same proof. So this is the performance. So we will have these well-known automated theorem provers as baselines. So these provers are called Z3, Vampire, and E. And we have the performance of tactic 0 here. You can see that tactic 0 is able to prove the most number of theorems, and it beats all the rest of them. Yeah, let me not just explain this in detail because otherwise there's just too much irrelevant information. Okay, so as we said, so tactic 0 is efficient, so essentially learns how to perform proof search, right? Because we have this concept of fringe and choosing fringe. So it's really doesn't do all the breadth first search or depth first search. Instead, it jumps between these fringes and choose one that's most promising. And how does it compare to the breadth first search and depth first search? The result is that it sits in between. So, it outperforms both, but in terms of the time steps and then the length of proofs found by these different proof search strategies, it sits in between. So breadth first search tends to find shorter proofs. Well, given a fixed amount of budget, so if you only allow the proof search to perform, like say 50 steps, then breadth first search tends to find shorter proofs, and depth first search tends to find longer proofs. On the other hand, breadth first search uses more time steps, so it needs to perform more tries. You can think of it, it has more errors. And depth first search uses less time steps. But our tactic 0, it has a moderate, it can find the moderate length of proofs, and it uses only moderate amount of time steps. So it sits in between. So the reason why breadth first search can only find shorter proofs is that it cannot go deeper enough, right? So if it can only go to a certain level of the tree search, then the length of proof it can find is only as deep as the proof search can go, right? So if you can only go like if your search tree is only say it has only 3 levels, then your the proofs found by your breadth first search can only be 3 steps long, right? So because each level is a step that's working, and depth first search is the opposite. It goes deeper enough, but it never restarts. So but the breadth first search restarts very more often. So you can see that the time step it takes is larger than the depth first search. Okay, so this is an example proof found by the tactic 0, and we compare it against the human proofs in the system. So this is a theorem which says that, and so this is a theorem about lists. So what it says is that given two lists L1 and L2, so I have a relation here R, which says that L2, L1 and L2 are related by R. What this means is that this says this relation, this every two says that this R is element-wise relation. It says that for every element in L1 and for every element in L2, R relates these two elements. So the first element of L1 is related to the first element of L2, and the second element of L1 is related to the second element of L2. And the theorem says that if this is the case, if L1 and 2 are element-wise related, then if I drop the nth elements of L1 and if I drop the nth element of L2, then the resulting the two resulting lists are still element-wise related by R. So this is the theorem that's not too difficult, but it requires a fair amount of reasoning to show that it's correct. So you can see that below this is the original human proof. You can ignore this kind of tactics, but the general proof strategy is that we do a proof by cases on whether n is less than or equal to the length of L1. And we do this kind of reasoning and we finish the proof. And the proof found by tactic 0 is a different strategy. So what it does is it performed a double induction. So it first do the induction on n, and then it's performed an induction on L1 because list is a inductively defined data type, right? So you can do the induction on the list. So this is how it is different from the human proof. You can see that another feature of human proof is that it uses a lot of unnecessary lemmas, while in the proof found by tactic 0, there is no lemma used at all. You only need to do the induction, right? So this is an example showing that the tactic 0 is not actually learning from the proofs in the library, which is exactly what we want, because this proof is not good. This is a lengthy proof and it doesn't compile fast. But the proof found by the tactic 0 is more concise and it is readable by human. It is more efficient. Okay, and this is another example of proof search. You can see that it is neither a breadth first search nor a depth first search, but a unique one, right? So if it is depth first search, you won't see nodes expanded on this this part because it will need to first expand the left part. It is not a breadth first search because you can see that this part of nodes is not expanded fully. So at this level, level 1, so only one node expanded fully, but this part is not expanded fully, right? So Yeah, but there's also some limitations. So let me just quickly go through this and tell you about the potential solutions to that, and we will finish the talk. So the efficiency problem. So the problem of this is that when we train the agent, we have to interact with the real proof engine, and the real proof engine usually takes time to perform proof steps. Some tactics may time out. You have to wait for the proof engine to finish. So the training is really expensive. It takes time. So for the agent of tactic 0, so we trained it for 2 weeks on a fairly good graphic card, and it is just and our experiments is not yet large scale, right? You can see that it only uses 1,000 proofs. So the problem is that it is not efficient, and because it is not efficient, we cannot really scale it up. And if we are not able to scale it up, it's not going to really learn good mathematics. The second problem is what we call the cut formula problem. So one of the problem with the current tactic 0 is that it cannot freely generate arbitrary expressions. It can choose from a fixed it can choose from a finite set of tactics. It can choose from a finite set of lemmas, but it cannot freely generate an arbitrary expression. So in mathematics, we often want to say that, in order to prove this, it suffices to show that, and it suffices to show that that is something you invented, right? It is an arbitrary logic formula, or say an arbitrary expression. And that is the sense of human intuition, right, or a sense of your mathematical knowledge. And in order for the tactics to be complete, to be able to solve any arbitrary goal, this kind of reasoning is needed, right? You always sometimes, so you always want to maybe invent new definitions or new notations, and that kind of capability is not there right now. So we want to solve this problem. This is what we call the cut formula problem, because it is what it suffices to show is the sort of cut formula, right? Okay, so these are two problems, and we have the potential solutions, but maybe they are too machine learning focused for this topic. So one thing we can do is that for this arbitrary, we don't really need to generate arbitrary formulas. We can fix a template, which is parameterized by some integers or whatever, or reals maybe. So you can fill in these holes, and you can use those templates as your possible suffices. That is one way, and we can also train this using reinforcement learning. But the problem is that those templates are hardly they hardly meet the requirements of general mathematics, right? So there is no fixed template that will work for every domain of mathematics, right? Your template for reals may not work for logic or whatever. So this is not ideal. They might be domain specific. So they might work for some domain specific tasks, but they are not good in general. So what is the general way? The general way is that we again use the language models. So what the good about language models is that they can generate arbitrary strings, including those suffices, right? So and to solve the efficiency problem, we will use model-based reinforcement learning. What does this mean? So this basically says that we can reason in latent space. So we can reason completely in those 256 vector space. So instead of reasoning in the real string space, in the real mathematics space, the idea is that we will learn a high-level representation of actions by embedding the raw actions into a latent space. We also learn a word model, so which is that we learn the entire dynamics of the underlying proof engine. And the dynamics is expressed in latent space, which means that it is expressed in those vector space, 256 vector space. So then the dynamics, so you take a goal, which is in the latent space. You take an action, which is also in the latent space. And the dynamics is given a goal and given the action, given the goal, given the lemma. So what is the resulting goal of that lemma application? that is also represented in the latent space. Now the entire math can happen in the latent space. The entire math is just in those real vector space, and you don't have to worry about the efficiency of your real proof engine because you will learn such a model. So you will learn the transition. How does it go from a go when it's given a lemma to the next go? So this is represented by just a function from R256 times R256 to R256. If we can learn this, then there's no need of the real proof engine anymore. And that would become a lot more efficient. And that is the general idea. Once we have such a latent word model, we can learn latent policy and we can do efficient planning in theorem proving. This is like saying that we are dreaming mathematics. So we are dreaming mathematics in latent space. And if you want to know this, if you want to know more about this, you can see our short paper at AITP 2021, which describes an early effort of this. It is still an early effort. It is still work in progress. But we know that such a model is learnable, but we still haven't had great success in finding a latent policy. But this is the current state of art, and yeah, this is the what I wanted to talk today. And yeah, this is an emergent field, and what we have now is that we know that it's promising, but it's still very elementary. There is no significant result that we can prove automatically using machine learning. We can let machine learning do, say, simple exercises from textbook if we have all the required lemmas in the library, but it is still not possible to find proofs for real math that you guys are doing. And yeah, that's all I wanted to say today. Yeah.
OK， 谢谢吴敏潮的报告。大家有什么问题吗？大概只能问一个问题。没有人问问题吗？那个短的证明未必是 readable 的吧？你能够
哪个证明？
前面你要保证前面那个列表里面那个有个表，就是前面在应该蛮前面了，就是一个列，就差不多就这样的证明，就是你当然你可以涉及到一个短就这个东西，就是说你这个一般你要找到短的证明的话，肯定要花蛮长的时间，是吧？就是，但是的话，OK。但你能保证这种短的证明是 readable 的吗？就是这个。
it depends on what readable means, right?
靠的呀，但是就这个确实很难量化，就是说你能拿一个证明出来，然后的话，那个你怎么保证？
So right. So sometimes you will have a very short proofs that use a very advanced tactic, and that advanced tactic can embody very high level like mathematical intuition, or it is a very complicated decision procedure for a certain problem. And then a lot of information is inside that tactic, but you don't really know what's happening for your proof, right? So yeah, that's a problem. That's true.
但这个我不知道有没有一些那个反馈，就是说，比如说你可以给一些unreadable 的 proof， 然后的话，可能不是因为它 unreadable， 是因为人们很难接受这种想法，就反馈到人类的话，会不会有一些就新的 idea 在里面？就是我不知道，但是这个因为我就反过来就给一个短的证明，或者一个完全不同的证明，然后让人能想到一个崭新的一个完全不同的思路来证明，给人一些新的启发。
Right, so it depends. So if you're only using tactics in the library, so if you're only using the tactics and the lemmas in the library, so all the new ideas that can possibly be is a new combination of these already known techniques, right? So there is no new techniques, right? So your tactics is what you already know. Your
但是
your
那
lemons.
个 some creative combination of this techniques.
It can be right if new ideas can be the new crazy combination of those things, then it can give you new ideas. Yeah. Also, the tactics, in principle, can be written by human authors. So you can develop new tactics.
Yeah.
And it is also possible to use machine learning to develop new tactics because these new tactics are just programs. If you can generate new programs, you can generate new tactics.
像围棋那种东西，它可能就完全改变，可能会完全改变一些当时围棋就人类认为的围棋的那种技术。我不知道。
Right, but essentially that is still just search, right? It is just neural network plus brute force search. And the good thing about search is that the neural network significantly trimmed down the search space. You just have a much more promising search space, but it's still search. So this is the same thing. So what we've seen before, so what I said here, the most successful one here is the GPTF language model plus search, right? So the language model only responds is only responsible for suggesting the possible tactics and proof steps. Most of the work is done by best first search. So it is really search that's giving you the good results.
OK， 那我们谢谢吴敏超的报告啊，然后我们再等个10点20开始吧，下一个报告。好，谢谢。
好的。